Welcome back to this course on C programming and assembly language. We are in module 3 where we are discussing how we can translate a given C program into its assembly output, right. So, and we are trying to compile the code here, which means we are trying to do task 2 that we alluded to in an earlier discussion. So, last lecture we stopped at this point where we translated the C program into its first order assembly output, which means we just translated all the ALU operations into their corresponding unoptimized compiled output, and we just saw what happens if the program were executed as is and what instructions needed to be added. And we saw that there were two problems that we encountered. One is stack corruption and the other is returning to a wrong address from the main, right. So, let us just quickly refresh ourselves on what we had discussed there. So, the function fn which basically took two parameters x and y got translated to the following assembly output, where EBP minus 4 is the local variable z in the function. Note that that same local variable same address EBP minus 4 is used even to access the local variable z in main, okay. Of course, the fact that both have the same name is not related to this discussion, right, but all local variables are accessed in exactly the same way, right. And z equal to x plus y translates to some simple move and add operations. So, the instructions in red are the unoptimized assembly output, which is a very obvious thing that from what we have discussed till now. The instructions shown in blue here are the ones that we had to add in order to do certain things, right. For example, the first instruction move EBP comma ESP, right, was to basically move the base pointer to the stack pointer, right. So, why was this done? This was essentially done to ensure that the context of the called function is being set correctly, okay. This is context setting, okay. So, the EBP, which was actually pointing to the local variable space of main before this, is now being made to point to the ESP, which is basically the new local variable space of the function fn, okay. And next we had to add another instruction sub ESP comma 0x40, and this was mainly to allocate local variable space. So that any stack operation like push or pop does not overwrite the local variables that we have been using in the function fn, right. So, then we went ahead and executed the body of this function, which are basically the instructions in red, and before we exited this function we had to undo all these operations, right, especially what we had done on the stack pointer. Otherwise, we would return to a wrong value when the RET instruction is now called. So, therefore, the sub ESP minus 0x40 had to be undone, right. So, if you see, this instruction is basically a pair. So, whatever you do with ESP in that instruction you have to undo here. Now, if you had more local variables, then the compiler would have basically done sub ESP minus some larger value, and out here before you return it would add ESP comma the exactly the same value, right. So, this occurs in pairs, and this is obvious because any operation that you do on the stack pointer has to be undone before you exit that function, otherwise you will be in trouble. And after that we simply did a return, right. And in spite of this we had two problems. One was stack corruption, right. So, after this return our instruction pointer would simply go back all the way to this point, right. After the return it would go back to this move EBP minus 4 contents of comma EAX, because that is the instruction after call fn. When we return from the function fn to main, unfortunately we have not been able to reset the context of the local variable space back to that of main. So before we went into fn, we were able to set the context to the new function by doing a move ebp comma esp. Unfortunately now we can't reset that, right? And why is that? Because before we went into this function fn, we did not care to save the value of ebp that it had originally. So therefore before returning from fn, there is no way that we can restore this value, right? Then we looked at another problem where we went ahead and tried to execute the function main, right? And the problem is the stack pointer esp is now pointing to the 0x0002, right? And what is that? That is essentially a value that we pushed onto stack, right? So as I mentioned earlier, any operation that you do with the stack pointer has to be undone before you come out of that function, and that is the exact problem that we are facing even now, okay? So what are the problems? The problems essentially are stack corruption, and the other problem is the function parameter push, it has to be undone. So this is what we want to achieve, and we need to add some more instructions out here in the blue region so that we are able to overcome this problem, and now we will look at what those instructions should be, okay? So let's again go through the execution of this function main, right? And as usual, the stack pointer and the base pointer are pointing at some arbitrary values that we don't know right now, and we do move ebp minus 4. So assuming that the stack pointer and base pointer have been initialized correctly, it is going to point to the local variable space of main. So therefore the local variable z in main gets set to 0. Now you push 4, you push 2, there is no difference from what we did earlier, and then we call the function which is at the address C200. So the return address C104 is pushed onto stack, and you move into the function fn. So now before we proceed with anything else in this function, what we need to do is to simply save the ebp value somewhere so that we can restore the context of main before we return from this function fn. So where do you store it? Of course you cannot use a register as usual, it has to be stored somewhere. Turns out that the stack is the best place again to store this. So before you do anything, you push the current value of ebp onto stack. So what gets pushed onto stack is actually the ebp of main now, okay? Now I do the same old operations that we had discussed earlier, move ebp comma esp, which is context setting, sub esp comma 0x40, which is allocating local variable space, then the function body executes. Note now that because I have done an extra push of ebp in the first instruction, the function parameters x and y have now got to be accessed as contents of ebp plus 8, because it's 4 bytes here, 4 bytes here, and then ebp plus 8 and ebp plus 12. Earlier it was ebp plus 4 and ebp plus 8. So now we need to add this, change this addressing a little bit, okay? Now you continue executing the body of the function. Now before you return from the function, you have to undo all that you did. So you add esp comma 0x40, which is the local variable space, pop the top of stack, right, which is basically storing the ebp of main back to the ebp register. So this instruction pop ebp now ensures that my ebp has moved back to the calling function's local variable space, right, which is that of main in our case here. Okay. So that solves one of our problems, which is the stack corruption problem. Now we still need to undo the function parameter pushing that we did, because now when you continue from this function and go back to main, ESP will still point to the wrong value. Okay. That is where the ret n instruction comes to our rescue. If you remember, I had pointed out that ret n not only pops the top of stack into the instruction pointer to resume execution from where it left off, but it also adds that n to the stack pointer. Okay. So the purpose of this is exactly for undoing the function parameter pushing onto stack. So note that just because we pushed two variables onto stack before coming into the function, it does not mean that we have to only pop these two values out to undo this operation. We can also simply add something to the stack pointer ESP and undo this operation. So what you do is you do a ret 8, and what does ret 8 do? It does two things. One is pops C104, right, and ensures that the instruction pointer has been loaded with the return address, which is C104, and in the same instruction also adds the value 8 to ESP. Why 8? Because I passed two 4-byte integers to this function. If I had instead passed three 4-byte integers to this function, I would have done ret 12. Now, like the earlier example, if we had 3 integers and 1 character, then I would have done ret 13, right. The ESP would have got added with 1 3. Now I go ahead and continue this particular execute body of the function, right, the body of main, continue executing that, and I can exit from my function gracefully. So in summary, the function gets translated to a function call gets translated to a call address, right. This is something that we already knew from microprocessor programming, but what we did not know is that we had to do a prologue and an epilogue. What is a prologue? It is exactly those 3 instructions that we added to store the current EBP on stack, which is storing the current context, setting up the stack, or initializing the EBP, right, or this is setting up the context of the function fn and allocating local variable space. These are the 3 tasks that happen in the prologue of a function. Then you execute the function according to its whatever the instructions are, and before you exit that function you have to undo this operations of prologue, and that is known as an epilogue, right. So what is the epilogue? It is basically setting the ESP to its original value and setting the EBP back to its original value before exiting that function, right. So how did we fix these particular problems? We went ahead and fixed it in the following way. So before we let me add that instruction here. Before we did anything in the function fn, we said we will push EBP onto stack, right, and before we return from this function, we were going to simply pop the value back onto stack, right. So these were the 2 corrections that we needed in order to execute our function fn in a consistent manner and go back to main without causing any context switching problems, right. And of course, to handle the function parameter pushing onto stack, we had to do this particular operation. Let me write that in a different color, right. So what did this do? This is stack cleanup. Right, and push EBP is saving the context. Okay, here the comment here, this is saving context. Okay, the next instruction move EBP comma ESP is setting the context for the function fn. The push EBP onto stack is saving the current context of the calling function onto stack, right. So, now that brings us to a very interesting question, which is, okay, in this function fn I had two parameters int x comma int y, and therefore I did ret 8. Okay. So, let us look at let us look at this function in particular. Int y, I did the usual things, and let us just focus on the ret instruction here. Okay, I am going to do ret 8. Now, suppose here instead I had int x comma y comma char c, then I would do 9. Now, if I had another integer, then I would do return 13 and so on, right. So, the question is, can I always do the stack cleanup in my function fn itself, right. So, that is the question that we want to answer. Clean up stack in fn always. So, what other kind of function are we used to? For example, let us look at this function called printf. Okay, the signature of this function is char star comma dot dot dot. So, what does this dot 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 mean? It means it is a variable argument list function. Okay. So, this is list. So, for example, if I wanted to call this in my main, then I could call it in the following way: printf some string %d comma some integer x, right, or I could call it as %d comma x comma y, right. So, depending on what my character string is and how many percents I have in that, I need to pass as many parameters to this function, and therefore, if you look at the implementation of printf, evidently it is not possible for me to do the stack cleanup by doing ret 8 or 9 or 13 or whatever, because the function printf does not know how many parameters it is going to receive upfront, right. So, you cannot do stack cleanup in printf, right. So, if you look at the function printf and you look at the implementation, it will have whatever the body is, but the return instruction will simply be RET. Okay? This, because it does not know how many parameters it's going to receive upfront. However, what the compiler does know is how many parameters the calling function is going to pass to printf, right. For example, in this main I have two instances of printf, right. I am calling printf in two cases. One is I am passing only x as an argument for the %d. In the second case I am passing x and y to two %ds, right. So therefore, these two calls will get translated slightly differently. Okay. So let us look at how this thing would happen, right. So I have the first printf, %d comma x. How will this get translated to assembly? Essentially you will do push whatever x is, then you will do push whatever this constant string is, right. This is a constant string, so you will push pstr. Okay. So somewhere in memory pstr is a constant string, is this particular string. Okay. And then you do call printf. Now when you return from this function, what you know is you have pushed 4 bytes, an integer, and you have pushed a character pointer, right, which also is 4 bytes, and therefore out here you do what is known as add esp comma 8. Now on the other hand, the same printf, when it is called as %d x comma y, will get translated as push y, push x, push another constant string, let me call it as pstr2 is going to be %d in memory, pstr2, right, and call printf. And when you return from printf, now you got to do add esp comma 12. So the difference between our earlier implementation where we did RETN and doing this add esp comma 8 or 12 explicitly is in principle the same thing, right. It's we are splitting the job of returning and adding a constant to the ESP in two instructions in this case, right. So here we are pushing the onus of doing the stack cleanup on the calling function, right, because it's only the calling function that knows exactly how many parameters are being passed to that particular function, right. So this calling convention and stack cleanup are sort of related, and you know you have a particular calling convention as they call it in Windows programming, right, which is __cdecl, right, where what this means is that it's by default this is the calling convention in C programs, by the way, okay, in C functions. It's needed for variable argument list like printf, and the calling function is going to clean the stack by doing add esp comma n instruction. _std call, right, is of course it is faster, I will tell you for what reason, where the callee or the function itself does its own stack cleanup, right, and this can be done only when the arguments are fixed and known at compile time itself, right. Of course, the std call is a little faster than the cdecl call because the retn instruction does two things in one shot: popping the top of stack into the instruction pointer and adding esp comma n, whereas in cdecl these two things happen separately and therefore it is marginally slower. Of course, when we go into assembly level programming, some of these marginal differences also can make a significant impact on our programming time, and therefore it is important to know this and pick the right one appropriately. Yeah, so in the next lecture we will look at what happens when we look at a C++ program at assembly language level.